Okay, PGAS panel discussion. So we talked this morning about users and applications and how those impact the underlying network infrastructure. So I wanted to take that to heart and start with a discussion about PGAS. So a gracious panel has agreed to participate, so we're going to hammer them to death with questions, see what we can get out of them. So let me introduce the panel. First of all, actually, I'm going to ask them to introduce themselves because they'll do a better job of it than I would. So if you guys would start from right to left, a one-line biography or maybe 5 lines if you like. Howard?
Hello? Okay. So I'm Howard Pritchard. I'm an engineer, software engineer at Cray. Is that better?
That's
much
better.
Louder. Okay. Software engineer at Cray, and I think Paul invited me to talk because in a former job, I worked on what's called a DMAP layer, and you'll see later what that is, but it was to support our PGAS compiler. And so I actually know relatively little about InfiniBand, except at a high conceptual level. And so I'm kind of here, I think, as an outsider saying how we tried to support PGAS on an RDMA-capable network.
Okay, my name is Mirko Rahn. I'm with Fraunhofer, and we are a user of OFAT in 2 senses. So we have our own internal wrapper, so to say, to make it easier for our internal users to make use of IB verbs. And we are developing applications for our customers, which are end-user applications, which make use of our internal wrapper. And I think I can give some input from that application view on what are the patterns that we use or that our applications have, and maybe what is an interface that we wish to see.
I'm Rich Graham from Mellanox, a solutions architect. In terms of PGAS, I think one of the areas that I had to contribute is when I was at Oak Ridge, my research group there actually was looking at. Oh, okay, I was told.
Let's pass the handheld around.
Okay.
We'll share a dirty microphone.
So Rich Graham from Mellanox in the architecture group, solutions architect. In previous life at Oak Ridge, I had a research group that looked at programming environments, programming models for exascale, and obviously PGAS is one of the areas that we looked at, so I have some experience there.
Hello, I'm DK Panda from Ohio State, and I've been involved in this OpenIB, Open Fabrics almost from the very beginning. We have been working on the MVAPICH to stack for the last 12 years. But today I'll be talking about some of the PGAS thing, what we have done, not only just supporting like UPC and OpenSMEM or the native IB verse, but we have a hybrid version where you can mix and match with the MPI, with UPC or OpenSMEM. So that is the kind of experience I'll be sharing today with the panel.
Hi, I'm Bob Woodruff. I've been involved with the Open Fabrics Alliance pretty much since it began. I have several people that work for me that you may also know, Sean Hefty and Arlen Davis and Stan Smith, who also participate heavily in the Open Fabrics Alliance.
Okay, thanks, guys. And I appreciate your being here. I appreciate your participation on this panel. So what do we want to get out of this panel? I started with the assumption that OFA members are networking experts. I think that's a fair assumption. And I also started with the assumption that we may not all be PGAS experts. Clearly, I am not. And to the extent that I'm not a PGAS expert at all, I'm probably a good proxy for those in the audience who are also not. So our simple objective here is just to bridge that gap between there's this application layer or a set of applications that use shared memory. How do they work, and what does that mean to us as network developers? That's the objective of the panel, is to try to understand what the impact on the network is, the underlying network is, of supporting PGAS. And along the way, we're going to ask questions about what the value of PGAS is and so forth. I promised each of the panelists 3 to 5 minutes to give a presentation. So let's start with Howard. Now, here comes the proof in the pudding. Let's see if I can actually find it. Okay, first I got to find the mouse. Go to my left. Is it getting close? Well, there it is. There it is. Oh, I saw it. I swear I did.
Bill is optimized laptop. Made it difficult.
There it is. I found it. Let's see. I'm looking for. There you go. Do you want me to flip slides for you?
Flip the slides.
Okay.
It's on? No, it's on. I should. On now? Yes, on now. So I decided after Paul, I thought about a little bit about what maybe would be most useful for this audience, and I decided to focus on the Cray UPC Cray Fortran compiler, because that tended to be the hardest thing for us to support, even on an RDMA network, which was, we think, well designed for this type of problem. And I'd emphasize that it is a true compiler. It is not like the UPC Berkeley. There's a front end that the UPC or Cray code goes through. It's translated to back end, and I'm not a compiler person. I was just told this is how it kind of works. Back end compiler to the back end, and the libpgas, which is maintained and developed by the compiler group, has detailed knowledge of the internal dope vectors and that type of thing that gets generated by the back end. And the libpgas, in turn, invokes the layer of software which I was active in designing, which, for historical reasons having nothing to do really with PGAS, we call DMAP, for Distributed Memory Application Library. So we have two main components. The compiler is the blue bubble at the top. The kind of pinkish area is the DMAP and the supporting kernel infrastructure, very similar to the slides we saw earlier with all the OFED stack, and the usual OS bypass on the right, and privileged operations going through the generic network interface device driver. One thing I would say that the compiler people told us was very important to point out. First of all, we are a Fortran shop still. Cray will probably be that as long as we're in business. So Cray actually proved to be far and away more challenging of the two models to support, and it's much more challenging than SHMIM. SHMIM is trivial compared to the problems of supporting a compiler. Next. This is just a summary of what DMAP was good at. We made sure we needed an API that was good for a compiler that generated a lot of very fine-grained RMA references, 8, 16 bytes, that kind of thing. They do have contiguous accesses, but since it's not like an active message-based technique, it's more like what you would expect on something like a T3E, if you know what that was. We had to optimize for those kind of network accesses, but we wanted to make the API general enough that it could exist over many different types of hardware over a significant amount of time. It's based loosely on concepts from Cray and Quadric SHMIM, and if you know anything about the Quadric SHMIM in particular, it had blocking, non-blocking, and non-blocking implicit types of operations, and if people have questions about that, we can talk about it later. One big difference from SHMIM, since IOMMUs are always complicated to implement, and we needed to be able to support general memory access, along with the usual arguments to the SHMIM API, it also had memory descriptors. Supports RMA read-write and atomic memory operations and strided and gather-scatter type operations. Next. One of the biggest challenges in providing the PGAS people what they wanted was in memory registration. So although the DMAP to help support SHMIM automatically registers like the data segments and a symmetric heap concept that we kind of get from SHMIM, we had to implement a much more general memory registration so they could access Cray Fortran, you can access any, it's legally allowable to access any section of another rank's virtual address space. We had, using the hardware, we were able to do things like make sure there was support for what we call symmetric memory registration. So you don't have to use different remote memory keys for all the different ranks. You have one remote memory key and it can be good across the entire job. Another thing we added recently was an idea of dynamic memory reservation, where you sort of pre-register a very large VM region, and then as you need to kind of fault in the pages and register specific regions, you have an update registration function. And just a side note, DMAP handles the registration of get buffers internally. And almost done. Next slide. Some other stuff we had to add for like ARM-CI was an active message queue concept. We also have a notion of collectives using something we call a PSET, process PE set, which is kind of like an MPI groups. And for customers on the East Coast, it was very important to make sure that multi-threaded applications could not only use the DMAP in a thread-safe manner, but also what they call thread hot, where multiple threads within like a pthreads application could all be efficiently accessing the network concurrently. And we added hooks to allow for progress of MPI and other. MPI could register callback functions with DMAP so that the MPI could make progress even if you were blocked in a DMAP call. And that's it.
Good. Thanks, Howard. Mirko.
So I do not have slides in order to avoid a pitfall to make just a promotion. Maybe I just talk to you or tell you what we are doing with IB verbs. So back in 2005 or 6 or something like that, we realized we are facing data sets that are too large to fit in single memory, data sets from oil and gas, which are survey data that needs to be processed and visualized. And we needed a way to access this data. And IB verbs remote DMA was a good solution. And to free our internal programmers from the complexity of connection handling and all this stuff that you have to do, we've wrapped it basically. This was the starting point. And then we used it internally for exactly processing and visualizing the data. And as time goes by, the interface evolved. And 2 years ago from now, we started to bring it to the public. The name is GPI. We are also involved in European projects to make an application level standard for accessing distributed data. And and last year we implemented it for Cray, not on top of DMApp, but on top of GNI. That's what I've for some technical reasons. And what we see is that we are successfully in producing scalable applications. Our customers are running applications on 200, 400 nodes on a regular basis. The end user is running applications. And maybe in the question and answers, I can give some concrete input about application patterns that we see.
Concrete input is what we're after. Thank you. Rich.
Okay. So I decided to take a slightly different tact and really not go into anything specific about what we're doing on our at Mellanox about this, because I view the state of the art in terms of PGAS programming models and how they relate to exascale. Things are still really evolving. I mean, it's still in the context of research, and to talk about specifically about how to optimize this or that for it, I think is not the time. I think the issues that we need to be looking at right now have to do more with longer term, how the direction that these things are going to take, because that's ultimately what we want to target. I mean, because things are still in the process of changing quite a bit. So all I have are really very high level comments and the like, and not the details on how to optimize this or that. And so right now, first of all, I think it's really important that the networking community, that we be involved in helping determine what these full programming models actually look like, not just how the data gets transferred, but some of the but start to address things in terms of how do we fit in well within the context of, say, of other threaded programming environments. How do we fit naturally from the applications perspective into these? Things like completion semantics and the like. How do they match well into to what is convenient for users to use, and yet at the same time be able to provide performance that is acceptable to the users. And really need to look at, to help and make sure that from a programming model perspective, that network access looks very much like just one more level in the memory hierarchy, and not something that's sort of off on the side that you have to treat differently. So in terms of how this might look from our perspective, from that of the I'm trying to remember what I wrote. From that of the programming model is again, I think data movement and synchronization. Users need to be able to express those sort of operations in a way that fits well with other memory accesses, their local memory accesses. From a performance and efficiency consideration, it's really important that communication stacks obviously be asynchronous. And provide the ability to overlap computation and communication, especially if predictions go as people have talked about, where it will be very important to be able to process very, very small amounts of computation very quickly. We have to be able to overlap communication and computation. And really, I think another big important thing here is and it goes along the lines of overlapping computation and communication, is really minimize the amount of time or amount of resources that the compute portion of the system needs to set aside for processing communication. Then from the application perspective, we think it's going to be very important to support fine-grained communication operations. I mean, that's the direction that things seem to be going right now. We'll see how well that materializes over time. And again, synchronization mechanisms for the user. It's much more convenient to be able to express synchronization with data that comes across the network in exactly the same way that you express synchronization with data that you got from another thread that's running on the system now. So I think that was all.
Yep.
So that's
Okay.
Okay, good morning. So here I'll be just trying to share my experience, as I said, like with the hybrid design. So as most of you know, our MVAPIS2 project, we have been working for many years. The latest version has MPI 3, as some of the people were asking in the morning. But the focus here will be how we can really combine MPI and the PGAS. And we started on this since last year. And broadly, our design is again, which is up and down.
Yeah, you go with the arrows.
Oh, here. Okay. So the broad thing, what we have tried to do, if you think of like the OFA verbs or an InfiniBand, it doesn't matter whether you're running an MPI or UPC or OpenSMEM or anything combined. So that's the kind of approach we took, so that we have a unified communication runtime here. On top of that, we have designed like not only like you have PGAS, like pure UPC or OpenSMEM. Obviously, MPI is already there. And then we can also combine with MPI with OpenMP with UPC, or MPI with OpenMP, and then also the OpenSMEM. And this has been like already is available in a downloaded form. Anybody can just download and use it. It has been there for since last year. So the interesting thing here is that what happens, and this is, we are trying to align with what Exascale people have been talking about, that with this kind of a hybrid model, you can mix and match. Because a lot of code has been written with MPI, a lot of code has been written with UPC, and a lot of also code has been written with OpenSMEM. So it is not that people will try to explore, like saying, let's say there is a UPC code, everybody will try to take that code and then convert to MPI or vice versa. So what we are thinking here is that this will provide like an incremental approach. So if you have different kinds of kernels, and if you see that some kernel is not good for MPI or not good for UPC or PGAS because of the regular and irregular, you can mix and match. And I'll show you some numbers. We have done that with the Graph 500 at the end, and it gives really good performance benefit. And this is what exactly is also the Exascale roadmap is talking about, like hybrid programming is a practical way to move forward for Exascale systems. So coming back to like Paul's questions, I'll just try to answer some of these things, the shared memory models. So basically, PGAS models improve the programmability, and especially for irregular applications, so that's why it has been designed for. And then the hybrid programming models allows the incremental application development using both MPI and the PGAS models. Now, in the runtime implementation issues, so we think that the runtime should provide the flexibility to choose between the PGAS and MPI, as we are trying to do.
So keep in mind that our audience hasn't seen these questions yet.
Oh, they are not?
Not yet.
Oh, you didn't say that. Okay, sorry. So I need to repeat. So these were the questions Paul had sent to all the panelists. So I can read them again. So with the implementation sides, the question was, each one of you have looked at various implementations or interfaces of PGAS languages. How have you implemented the interface? What has your experience been with it to date? So this is my answer that runtime should provide flexibility, and it also should address a core set of issues. And when we come to the core set of issues, as we have been discussing, it's the, let's say, the InfiniBand layer is mostly the network usage, memory usages, and can you really handle those in a scalable manner? And that's what exactly the unified runtime does, so that you can actually not only offer deadlock-free communication, because many times when you put these programming models, they have their own programming asynchronous progress, semantics, and if you just put them together, you are not guaranteed that they will work. But whereas if you do a unified runtime, then you can handle that. And it also provides better performance and optimal network usage. And what we have done is, like, under the hood, we have designed all these things using one-sided operations, atomic, synchronization, active messages. So all these things, whatever people have been using, so we have taken that at the underlying layer.
DK, let's hold off on these.
Okay.
So we'll go through these and let the panel chew on the questions as a group.
So we'll skip these things?
Yeah.
Okay. So then let me just finish this. I'll skip this, but just try to finish this here with some performance numbers to show like these kind of things. Like, let's say this is trying to show some numbers with the OpenSMEM. So obviously OpenSMEM GasNet, there is a open source version out there, but it has not been really optimized for open fabrics. And that's what if you see, this is the OpenSMEM OSU version. So here if you see atomic, broadcast, collect, reduce, all these things, we can deliver you much more performance. And finally, like the hybrid model, so this is a paper which is coming out, will be presented at ISC in June. So what we did is, like, we took the Graph 500, and for that application, we tried to explore, like, people have done some of these MPI designs, like MPI Simple, MPI CSC, MPI CSR, but all these don't scale. If you see here, either from the execution time or strong scaling from rescaling, they're not doing it. So what we took is, like, just took one module out and then converted that into the OpenSMEM and put it together. And that our hybrid runtime can support. And now you see that up to 8,000 core, this was run on Stampede. We can give you like almost 2.4 times better improvement in the execution time. And the scalability wise, if you see, it strictly goes to like 8 to the power 10 to the power 9. Kind of, this is the traversed edges per second. So nobody else in the MPI domain has been able to reach to that higher value. And that is the kind of benefit which this hybrid programming brings.
Thanks.
Thanks.
I don't have slides, but I can just say a couple of words.
So we have been looking a little bit at the PGAS space, just more from an investigational perspective to try and understand it better, because we understand that it is important. One thing that I've definitely seen, though, is that it seems like in the PGAS space, once you get down below the compilers, UPC and Cray, Fortran, into the runtime space, it's really fragmented, right? I mean, there's a lot of different runtimes. You got OpenSHMEM, there was the PAMI interface for the Blue Gene, there was the Fraunhofer stuff. So it seems like, you know, everybody is solving a lot of the same problems, because once you get to the attributes that are needed by the PGAS languages, they're all the same. You know, it's one-sided communication. You need certain, you know, types of collectives and whatnot. So, you know, as you had mentioned, you know, it seems like the PGAS space is still under construction. I think there's maybe an opportunity for the community to get together and try to unify some of the, especially the lower level runtime stuff. Because if we were able to do that, again, as Bill Magro was presenting earlier, if you have a defined API with a definite set of semantics, it allows the hardware vendors to then target that. If I have like 5 or 10 different runtimes, and I'm a hardware vendor, I'd say, well, which one of these do I optimize for, right? I don't know, right? So that's my comment there. There's an opportunity.
All right, good, thanks. We'll just leave that up there. We'll pass it back and forth. So I did prepare, as DK pointed out, he stole a little of my thunder, but that's okay. You know, half a dozen or so questions. We are not going to get to most of them by any stretch of the imagination. So let me just pick on one or two that I hope will get to the heart of the matter, and then I'll turn you guys loose and let you chew on that question, and then we'll move on to another one. Maybe we'll get to 2 or 3 of them. I did have a question about, you know, the value of PGAS, but I'm going to leave that aside for now. I want to get right to the question of what the interface is. So I barked on this morning endlessly about using the application to define the characteristics of the underlying interface, and then what that means in terms of the low-level implementation of the network. And the particular model that I've picked on here, just as because I know it'll be provocative for some people, is GasNet as an interface. So is GasNet an appropriate interface, for example? I don't want this to be a discussion about GasNet, guys, but I do want you to talk a little bit about the possible interface implementations and what your experiences with them are. So was GasNet appropriate or not? What other interfaces have you used? What makes the most sense? And let's do this with an eye towards defining what the underlying network protocol really needs to be. Any thoughts on this, panelists? By the way, as Dr. Panda said, they all saw the questions beforehand, so everybody should get 100 on this test.
Is it on? Yes, it's on. I'm not like I said earlier, I'm not the compiler guy, but our compiler people sent us a voluminous amount of email back when my colleague Igor and I asked about GasNet. They did not like it. They did not like the model it essentially was used. It was, and I'm no expert in GasNet, but they did not like the concept of within a node, everything being threads and within a single process. And then the only time you needed to explicitly access the network was when you were going between nodes. And they used that model on our older systems, our XT systems based on portals. And there, the performance difference was like an order of 10 between a typical MPI application and a UPC or Cray Fortran application. And it's flipped since we dropped GasNet and went to our own software.
Which was DMAP.
Right.
To relate it to you earlier.
Right. So, for instance, for certain, for GUPS, table toy, you know, it's easily an order of magnitude or greater. It's the type of things with graph problems that TK was showing earlier.
So there's a vote for one interface other than GasNet. Other guys? Panelists?
As far as the impedance match between like the languages and GasNet, I really can't comment to that because I'm not a compiler person. But we did just as a comment that we did do a little bit of analysis of, for example, the implementation of GasNet over verbs. And since you know, InfiniBand or RDMA verbs provides the one-sided communications and such, it looked like the impedance match was actually pretty good from the standpoint of performance, right? If you look at the actual number of cycles that it takes to actually, you know, start a transfer from the GasNet down to the verbs, it was actually pretty good. Now, there may be some other issues with GasNet, for example, over verbs with respect to scalability that we've already talked about with respect to queue pairs and things like that, not scaling well, but that was the one observation that we saw of GasNet implementation, at least over verbs.
So that was over an IB conduit.
Yes, that was over an IB conduit.
Which I haven't shown in my picture. I should have. There's a mistake on my part.
Sayatan Sir did some performance analysis.
But what he's talking about is a
year.
little line that would extend from the GasNet API straight down to the verbs layer.
Yeah, so I think it is not the question of like whether the GasNet API is good or not, but the question is how best you implement that over the verbs, like as you were saying. So that's what actually we did, because now with the verbs, you have so many different choices, and especially all the different MPI stacks. I mean, they have gone through so many years of experience in trying to have the best implementations, and similar kind of things can be actually taken and then bypass some of the layers, intermediate ones, and deliver the best performance. And that's what we have actually done. Like the OpenSPAM, the OSU version, whatever I showed, performs better than the OpenSPAM with GasNet.
So I'll say that I am not a compiler person, even though we've looked at issues around programming models. So I can't comment on the interface between the compiler and the library, but I have looked at GasNet some. And one of the things I liked about GasNet is they do have a lot of nice primitives to let you decide how much cost you want to pay in terms of synchronization and the like. So they allow for bulk synchronization. That is, you can synchronize on a number of operations rather than operation by operation. But they also have the operations where you can synchronize one at a time. So I do like the freedom that, at least at the API level, that's been provided there.
So just to state the obvious, I've heard each of you guys say up here the same thing I said. I'm not a compiler expert. But one of the takeaways that I think I'm getting from this is we do need to engage the compiler writers as the users of Open Fabrics in this case and ask them what is the best way that they would like us to implement whatever they need in terms of supporting PGAS or something PGAS-like, just to state the obvious.
But maybe even one step before that, maybe even before they write their compiler.
Hopefully before they write their compiler, yes. It would be nice to write compilers for and not write the compiler next. Agreed. Okay, thank you. I also wanted to still trying to dig at this question of, what is the application, or in this case, a PGAS compiler expecting, in terms of the interface. Maybe we can gain some input as developers by asking this question about what are the typical, access patterns that you see of remote memory generated by a PGAS compiler. Again, none of you are compiler writers. I get that, but can we get anything out of this in terms of, well, it's small message or large message, or so? Anybody have any comments they want to offer on that?
I can give a couple of comments.
So what we understand from our investigations, there's a few attributes that are pretty common. There's a high volume of small messages. The PGAS things tend to be fine-grained parallelism, so it's a lot of small messages. So latency is very important. Message rate is very important. The amount of instructions that it takes to actually transmit the data or get it started is important. You have to do a lot more frequent synchronization points, memory consistency synchronization points, and those have to be very fast as well. And then one other note is in some of the fabrics today where we have things like adaptive routing, and the memory consistency issue, you have to be careful that the adaptive routing doesn't break the memory consistency synchronizations.
Maybe a remark from me. There's not only compiler, there are also applications, and I know about the application patterns, and with GPI we directly transfer the application patterns to a communication pattern. And I've written down 4 patterns that we are using or that we are facing. One is a neighborhood update. So that means a component has connection to only neighboring components, while the neighborhood relation can be static or dynamic. And the messages could be small, could be many and small. The application can do something again this by packing and unpacking the data. This is one pattern. The next is we have a global N-to-1 pattern using atomics for doing just load balancing. That means you have just a number of what's the next work package somewhere. It's an atomic, and all the components access that atomic. So it's a global N-to-1 pattern. It's a bit harder than the local thing, I think. What we also see is the global N-to-M read pattern. Means we have basically a database in memory, and all the nodes needs to read from that database in chunks of, say, 4K, something like that. And what we also have is the global all-to-all update pattern. That means all the components hold a part of the final result and produce updates to all that parts. Yeah? That means I have to say, one component says to another component, I have an update for your part of the final result. Please do it. And all components are doing that at the same time. And the size of messages in that pattern is around, say, 4 megabytes. So these are large messages. So this is what we see in applications. These are critical patterns. We have more, but these are critical patterns. And of course, they could be mixed somehow.
So pretty much everything you've heard, I would have said too. One thing our compiler group has found useful, and we actually could make it more general, but we don't want to cause too much API bloat. If you have a really good compiler, it can pattern match a loop, right? It will see a loop with a certain stride, particularly with Fortran, and if it can pick out like an API function from your remote access library that says, oh, I'm going to stride every 25 integer offsets into this array for a get, for instance, an RDMA read. That helps. It's a lot better than an IOVEC. Just say no to IOVECs in this space.
All right, let me move on to a question that I hope is maybe a little closer to the heart of the issue. When I think about InfiniBand, and I said earlier this morning that it seems like it's largely a one-to-one relationship. You're passing messages from one instance to some other instance, and to do that requires an exchange of memory keys between those two instances. So there's one key for every pair of instances. And Howard, you just said something a minute ago that I thought was sort of interesting. It had to do with a global key, so to speak. So let's ask a question about memory protection. You look at the current InfiniBand architecture, and it defines its system of memory keys and how those keys are exchanged, again, connecting a pair of instances together. The question I would have is that really an appropriate model for a PGAS implementation, or do we need to look at some other kind of a memory protection model to make PGAS really effective?
So the ideal thing would be if the you didn't have an IOM, well, the IOMMU on your NIC could walk the page tables if you were using a Linux system, and so it could walk the page tables of the process, and the application could work with virtual addresses, which is much more natural to a compiler or to an application writer. But of course, that's an ideal world. I think the concept we use is very similar to the portals table index in the OpenSHMEM version, where you sort of have one kind of sort of like a port number across all of the ranks in the job is for instance, the data segment. I think that would be a very useful concept for some IB2.
So in our OpenSHMEM design, so what we have done is basically it's like the problem is how do you assign the symmetric memory regions, and then each processor is trying to find out where the symmetric regions are. And most of the time, I mean, you need to do it in the initialization time. So we exchange all the keys and all at the initialization time. So it is not being done in a dynamic manner, so you don't really see the performance overhead. And also with respect to registration and all, even all the MPI stacks currently use the registration, like a registration cache, delayed registrations, all those things can be used also here. So just like what we have MPI, we have scaled to like up to 200,000 core, 250,000 core. So here also we can scale to that number. But if we are talking again beyond like a 2 million, 5 million, 10 million, I don't know what is the upper number. So there could be some issues. But if we can scale the MPI with using the current queue pairs and all those things, so I think here also we can do the same.
So in your view, then, the exchange of queue pairs between a pair of corresponding agents is not really a scalability or limit as far as PGAS goes?
Yeah, I mean, that's what we feel. If you do it at the initialization time, if you do it in a dynamic manner, of course, you have to have some overhead. And then you can use some of the other techniques like the registration cache and all to alleviate some of those bottlenecks.
I think just one thing in general with respect to memory registration is that, it's expensive. And you mentioned, the MPIs. Well, we worked around with, we have a memory registration cache. Well, it would be just nice if like you had mentioned, we didn't have to do this explicit memory registration. Somehow it was more dynamic, handled by the adapter and the operating system. Or number two, make memory registration free, fast, make it a speed path operation.
Good. Let me put you on the spot. Any thoughts about how to do that? Make it free or fast?
I don't know how to make it free or fast. I'm not the hardware guys need to figure that out.
I was just hoping. Any other thoughts on this one?
Well, so I would say in any case, as you scale very large up in scale, your communication patterns start to be sparse, and if you take advantage of that and really do only what you have to, you don't have to lose the flexibility of what exists today. Of course, it would be nicer if there are much cheaper ways to do it.
I would kind of disagree, Rich, because one of our main customers has a GUP-style application, table toy, and table toy has no sparsicity to its reference patterns whatsoever, and that's, I think, all of these schemes where you have to, I mean, in MPI it doesn't really matter too much because an MPI message is going to take a microsecond to go somewhere, whereas if you're talking about fine-grained accesses that bounce all around, and this kind of is somewhat distinguished from the applications y'all have, but particularly in UPC, where if you know how UPC works and you kind of can quickly go through whole arrays across the whole job quickly, at least when you're addressing, it's really a challenge when you have to have all of these keys, keeping track of which key to use for which memory registration. It's a mess.
So there's a vote that says the notion of a one-to-one memory key exchange is probably a limiter, or maybe a limiter. So I'm hearing two votes here. One that says this is fine, exchanging memory keys works okay, it scales okay. Another one that says maybe not in all environments. Anybody want to respond to that?
Well, I wouldn't disagree with Harvard. There are applications for which that's not true, absolutely.
Okay, so again, getting to the question of what does the underlying network have to look like or have to do, and where do we want to take the network in the future, it sounds like it would be good if we could support something that did not depend on the exchange of keys. Not to replace what we have today, but to augment it. How important is that? Is that high importance, medium, low?
I'm just going to make a comment here. The T3 series did a shred foot in, I think it was 3 or 4 cycles. Having done some research on this, if you're doing key exchanges, you're at a couple hundred instructions because you have to look those keys up and then put them. So when the gold standard was 3 and you're putting in a couple hundred, that kind of gives you a design goal quite right now.
So there's a pretty compelling vote in favor of let's avoid exchanging registration keys.
I think we
Okay.
reiterate that as well.
Any other thoughts from the audience? This is great. Bob.
Yeah, so I think MPI programs and such, they have a concept that, we'll do all this work up front, like it would take a long time, so it's optimized, and when we're running the code for a number of hours, the things are loaded. But these startup overheads are a big problem for certain applications. You really want to drive that latency down and make it lightweight for certain classes of applications. And so that class might be a simple communication that, between pairs that you want that to be fast and lightweight, but it could be lots of pairs. So one of our biggest problems is, somebody wants to run an experiment that runs wide on the system. The startup of that can take, minutes or half hours, sometimes longer, right, to get everything set. So you kind of want that to go quickly. And I know that especially in HFT and database, the latency of these setups is a real driving factor for issues that they're trying to solve.
So I'm going to encourage us all in terms of the 3-column chart that I described earlier this morning to try to characterize the requirements that you're all articulating that can be added as a line on that chart. Maybe it's under scalability, maybe it's under usage, I don't know. But the one you just mentioned, Bob, is a good one. The one about, it takes, 3 cycles versus 300 cycles, that's a good one. The exchange of memory keys and so forth. Let's put all those on that chart, and that'll go into our thinking where at the end of the workshop we can put all that together. I think we have time for one more quick question, so let me choose carefully here. Well, here's a good one. What are the strengths of PGAS as an idea, and what are its weaknesses? Got to keep your comments short and to the point, guys. We only have a few minutes here, but now's your chance.
I think the strength of PGAS is, on one hand, is that it allows the programmer to code in a style that's a little bit more familiar to them. Like I can just move data with A equals B, and it's there. I think the weakness is that you think you can just program just like you always did in a shared memory machine, but if you don't pay attention to the new aspects of the remote memory and stuff, you may not get the good performance that you think you're going to get.
Yeah, so the strength of the PGAS, as I said, it's mostly for irregular application. If you don't understand the pattern, so this is where the PGAS models really come into your rescue. If you have understood the pattern and all, MPI and all is good. But then the challenge is on the implementation. You can do much more easier programming, but then can you really extract the performance? And if those two things can be put together, then that is the best benefit you get.
Yeah, I would say in terms of strengths, if you have a good analysis tool, a good compiler, you can certainly eliminate a lot of overheads. Like I think the biggest weakness is it's really a SIMD model. And so, I don't know of a way to use MIMD type of, run at MIMD type of applications with a model like this.
I would second what Rich has to say about the SIMD. That's one of the weaknesses. And so, for instance, if you have a client-server application or something more complicated, not that I would necessarily, well, that's probably, for instance, I don't know what exactly you were supporting, Mirko, but that's why we ended up kind of going with 2 APIs, one for more dynamic, we thought of at the time, MPI2. So MPI2 supports this notion of dynamic processes that can come and go. Also, it's easy. It's a lot easier than one would think for a naive co-array or UPC programmer to get in trouble with synchronization, because it's actually, if it's a complex synchronization procedure they're trying to do, they can easily make mistakes. Common mistakes that someone who has to deal with multi-threaded processes would never do, but they don't think about it until you end up having to debug their problem for them.
So I guess actually I do have another couple of minutes, and that leaves me with the one serendipitous question I would like, and I'd like to put this to not just the panel but the audience as a whole. So some of the things that I've heard just in the past few minutes suggest some pretty significant changes to the way the underlying network protocols work. So the memory registration one is the one that sticks out for me, but there are other examples like it. Getting those changes made through the underlying networks is probably non-trivial. The question is, how important is it to us as Open Fabrics that we provide top-level first-class support for PGAS? In other words, how hard do we need to push on the networks beneath us to adapt to what we would like them to do for PGAS? How important is PGAS to us as Open Fabrics? Any comments either from the panel or the audience? If no one cares, then we'd be wasting our time and we'd be burning credits with standards bodies I'd rather spend elsewhere. But if this is really important, by all means, let's take it to the mat and push them hard and get what we want out of it. Any comments? Sumantra?
Thanks. So what I'm not 100% sure is about the PGAS support stemming from compilers. Because as it is impossible to change compilers, it is close to impossible. So I would rather see, PGAS, coming up as a concept, as a library, rather than, built into the language itself. And then application can pick and choose how best to use it.
That makes perfectly good sense to me. But still, if you think about it in terms of, an abstract library on top of, the question is how much do we provide in the underlying protocol that makes it easier for the compiler? You're right, we won't change the compiler. It's going to do what it's going to do. The question is, to what lengths do we need to go in order to accommodate the compilers the way they're written? And that's the question I think you articulated.
I'll make a quick comment, I guess, just one quick one.
So my comment, again, it gets kind of back to what Bill Magro was saying earlier about if we define a runtime that provides a really good impedance match to what the upper level compilers want, or in the case of somebody just writing a PGAS application to the runtime, if you provide that API and that interface, then you leave it up to the hardware vendors to decide how much of that lower level implementation they want to optimize, right? Be it through an IBTA standard or some other body. But at least we're taking the tact of the top down. We're providing the smallest code pass, the best impedance match between the upper levels, and then down below, people can innovate in the hardware to provide the capabilities that they want and they think they can sell, depending on how important and how big the PGAS market gets.
So that's a vote for a perspective I've heard articulated before, that it's really about defining that interface layer, and then whatever happens below it happens below it. Now, I would take a little bit different, I'm going to be a panelist for just a second here, a little bit different point of view and say it's fine for the hardware vendors to innovate around it, but there may also be a role there for standards to play in how they innovate.
Yeah.
DK, I think you get the last word here, then we're going to wrap it up.
Just to clarify one's question. So I think in the PGAS, if you think of UPC, it is a compiler driven, but if you go through OpenSMAM, it is a library, just like what you are suggesting. So in the community, these two directions are emerging. So is a library-based approach is good, or a compiler-based approach is good. So from our design perspective, we support both kind of things. So just to see how Exascale community want to move ahead with any of these approaches.
And I think that's the last word. Thank you. Thanks, guys. Thanks, panelists.